right, so there are three main states of matter, as you know, solids, liquids, and gases. And in this chapter, we're going to specifically focus in on the behavior of gases. So the kinetic theory describes gases and their behaviors. So we know that matter consists of tiny particles in constant motion, and in a gas specifically, the particles are very, very small and they're really spread apart. So one thing that's really important about gases, and this does not apply to solids and liquids, is that the gas particles, the individual particles, occupy an insignificant volume. In other words, if I think about how tiny a gas particle is in comparison to the giant space that that gas particle is in, does it really matter if my gas is this red dot or this red dot, right? There's so much empty space between them that the size of the individual particles doesn't matter. So that's what they mean by they occupy an insignificant volume. That would not be true in a liquid, right? If we think about a liquid and the particles are really close together, big particles are going to be more crowded than smaller ones. Or in this case, you could fit more of the smaller ones. So the volume would change. The volume of very small particles would be much smaller than the volume of very large particles in a liquid or in a solid. But that's not true for gases. The second thing is that there are no attractive forces between them. In other words, gases just float away, right? If I open a container of helium, the helium just floats out. And that doesn't happen with liquids either, right? If you have a beaker of water, the water doesn't just float out into the air. The water, there's attractions between the water molecules that prevents them from escaping all at the same time and just floating away into the air. So with gases, there are no attractive forces between those individual particles, and there's lots of empty space. They are moving very quickly. It's a rapid, constant, random motion, and they're going to fill whatever container they have. So if I take gas that's in a little tiny tank and I transfer it to a bigger tank, the gas particles are just going to spread out and fill the bigger tank. There'll just be more space between those individual particles. Additionally, they move in a straight line. Think about like when you play pool and you hit a pool ball and it goes straight until it hits something. That's the same thing that's going to happen with gas particles. They're moving in straight lines, just bouncing around inside their container. The collisions between them are what we call elastic. So that's kind of a physics term. It means that they don't stick together. So when I have one gas particle and another gas particle and they collide, they bounce off each other and they keep going. They don't stick to one another and then, react or form something different. So that's what they mean by elastic collisions. And the total kinetic energy, the amount of energy in a gas, which, by the way, happens to be measured in joules, it's constant. Even though when they bounce into one another, they may individually be transferring energy between them, we can measure the energy of the entire gas sample in joules as one constant measurement. All right, so one of the variables that we'll talk about with gases is the variable of pressure. So whenever the gas hits an object, it exerts pressure on that object. And that's because you have billions and billions of gas particles all slamming into the object at the same time, and that's what creates pressure. All right, and so if there's not any gas particles in something, then that creates what we call a vacuum. And if we think about space, outer space, it's almost a perfect vacuum. Even though there are some gas particles, they're so far apart, there's so few gas particles, that you have almost a vacuum in space. And what would happen if astronauts were not wearing pressurized suits is that literally your body would explode because there'd be no pressure pushing against your body to keep it together. So that's really, really important. Alternatively, if you were to go underwater really deep, like if you're a diver, you may be aware of this. So atmospheric pressure is the gas particles banging against everything in the atmosphere, right? Including the ground and you and all that other stuff. If you go up a mountain, the pressure decreases. It actually makes it harder to breathe because there's less gas pressure and less oxygen particles being kind of forced into your lungs. But additionally, if you go diving, what happens is when you go dive deeper, the pressure increases and it actually forces gases in your blood, some of them, to dissolve into the liquid blood, right? But when you come up, they're going to go back to gas again. And particularly nitrogen, if you come up too quickly, can form gas bubbles in your blood, and that causes something called decompression sickness or the bends. So how do we measure pressure? Since pressure is one of these important factors that gases possess, how do we measure that? So a barometer is actually a tool that we use to measure pressure. Now, an old-fashioned barometer, they used to be made with mercury. You see now today we have like digital ones and stuff like that. But the way that it would work is that the air pressure outside would be pushing down on the mercury here. You'd have a vacuum in here, so there would be no gas in here. And this also is pushing some. But the force of the gas from the outside would then force the mercury up. And that's why one of the units for pressure is mmHg, or millimeters of mercury, because we literally measured how many millimeters this would be forced up the tube. And it turns out standard pressure, in other words, if you do this at sea level, which is where our pressure is, that's kind of our standard pressure, it turns out that that ends up being exactly 760 millimeters of mercury. So that's where a barometer would read at sea level. Okay, so it turns out, when we're doing certain measurements, a lot of times measurements have to be taken at standard pressure. Now the standard metric unit for gases is called the Pascal, PA, but there are actually lots of units that we use for measuring gases. So standard pressure, as I said, at sea level is considered standard pressure. So sometimes you may remember in the last chapter when we were doing stoic, we talked about gases at STP, if you remember, and that was standard temperature and pressure. So standard temperature, which is going to come up later in this lecture, is exactly 273 Kelvin or 0 Celsius. Standard pressure is actually, I'll put it up right now. Sorry, let me erase my work here. Standard pressure is all of these actually. 1 atmosphere, which is the same thing as 700 millimeters of mercury. In pascals, the standard metric unit, that would be 101,325. There's another unit called torr. It would be 760 torr. Or PSI, or sometimes it's written this way, pounds per square inch, like how you measure, for example, pressure in a tire in your car. That's 14.7. So all of these are equal to each other. So what I wanted to show you in this lecture, our first math conversion thing here, we're going to use dimensional analysis like we used in stoichiometry to convert between pressures. Now, any one of these pressures is equal to any other one. One mistake people make with this is they think that like this can only be converted to the one next to it. That's not true. I can convert from millimeters of mercury to pounds per square inch in one step. Since all of these are equal to each other, it would be sort of like saying 12 inches is equal to 1 foot, which is the same thing as like 1/3 of a yard. Like you could have all these and they're all equal to each other. They would be different representations. So let me show you how to do these problems. So the first one, 98.7. So just like we've been doing in like the last 3 chapters, the first thing you're always going to do is you're going to write the number that you're given. So 98.7 kPa, kilopascals, times, on the bottom, we're going to put kPa, because remember, whatever's on the bottom is going to cancel. And then on the top, we're looking for ATM. So we put what we want to cancel on the bottom, what we want to look for on the top, and now we're going to go to our conversion chart here, and we're just going to transfer our numbers. Sort of like how in stoic, you would take your coefficient, and the ratio would come from that. So kPa is here. So that's going to be 101.325. Sometimes we just write 101.3. It probably won't change your answer by much if you drop the last part. And we're going to ATM. So 1 ATM is the same as 101.325 kPa. Our kPa will cancel, and our answer will be an ATM. Now, to speed things up, I actually have the answer to these first 3 problems. So this one should be 0.974. Now, just a heads up, sig figs, right? We want to use the same number of sig figs as in our original number, not the sig figs from our conversion factor. Conversion factors have a unlimited number of sig figs, so we're not going to round this to 1 digit because of the 1 ATM. We're only using our measured number, which is the number they gave you. So in this case, we get 0.974, 3 sig figs, because this has 3 sig figs. Let me show you one more. So 775 millimeters of mercury, so you do this, mmHg, millimeters of mercury. We're converting from millimeters of mercury, so that's going to go on the bottom, so it'll cancel. And we're converting to kPa, which happens to be right next to it, but again, even if it wasn't, it wouldn't matter. So kPa on the top. So we're going to put 760 on the bottom. Why? Because that's our relationship. For every 760 millimeters of mercury, there's 101.325 kPa. Now for this one, you're going to have to multiply and then divide. So you'd multiply 775 times 101.325 and then divide that answer by 760. And if you do that, you should get 103. And then for our last one, we're going from ATM to millimeters of mercury. Again, these do happen to be right next to each other. But if I wanted to convert, say, from millimeters of mercury to PSI, I could do that. I could convert from any one thing to any other thing using this same technique. So in this case, 0.950, this 0 is significant, so this will be 3 significant digits in our answer. The 0 before a decimal is not significant. So we're going from ATM to millimeters of mercury. ATM, atmospheres, will cancel. And then our relationship, we go to our conversion chart here. 1 ATM is the same as 760 millimeters of mercury. And when you multiply that out, you should get 722. So that's how you do basic conversions. If they say give you millimeters of mercury, but they want your answer, say, in kPa or atmospheres or something like that, that's how you would convert from one unit to another. Okay, so there are 4 variables involved in measuring gases. One is the amount of gas. That's going to be moles. I know everybody hates moles, but yes, it's going to be in this chapter too a little bit. So moles, the variable is the letter N, and you can get moles. If they gave you grams, you could convert to moles. If they gave you particles, you could convert to moles using the same conversion factors that we learned back 2 chapters ago. Second is volume. V is volume. That'll be the volume of your container because the gas is going to fill whatever container you're using, and we usually use liters as our unit for that. Temperature is going to be in Kelvin. So if they give you Celsius, you have to convert. We'll provide you with the conversion factor just to make sure that you remember it. But if they gave you Celsius, you have to convert to Kelvin. That's because, well, for one thing, kinetic energy is only proportional to Kelvin temperatures. But for another thing, it'll mess up your answers because remember, Celsius is actually just based on the boiling and freezing points of water. So Celsius has negative numbers, but that doesn't happen with Kelvin. 0 Kelvin is supposed to be absolute 0. You can't go any lower than that. So it's only Kelvin will work proportionally for calculations. All right, and lastly, pressure is going to be P. We talked about that gases exert pressure. Typically, kPa or ATM are the 2 pressures that you see, but you could be given a gas in a different unit of pressure. Okay, so what we're going to talk about in our next lecture will be some of these different gas laws. So for example, this is called Charles's law, and as you can see, it's the relationship between volume and temperature. So when I heat something up, what happens to it? Oh, well, if I raise the temperature, the volume increases too. So it forces this to get bigger. Another law we'll be talking about, going back here a little bit, is Boyle's law. Boyle's law is an inverse relationship, and it's about volume and pressure. So if I increase the pressure on a gas, notice they're adding weights to increase the pressure, the volume goes down. It smashes the gas into a smaller area. So if one goes up and the other goes down, that's an inverse relationship. If one goes up and the other one also goes up, that's called a direct relationship. So that's what we're going to be focusing on. Pretty much the whole rest of this chapter will be all the different gas laws and how they relate these 4 variables together.